welcome back. We are in the second video of this section. In the first video, we talked about this example here. Say you have some action figures in cereal boxes distributed randomly with this distribution, and we want some hallops because we like her game. We determined that the probability of getting 3 boxes with Simona Halep in them out of 3 boxes, so getting all 3 with the right one, is going to be the probability that she's in each individual box times itself 3 times, or 0.2 to the 3rd power. We also determined the probability that there were no Haleps, no successes, in the other 4 boxes was 0.8 to the 4th power, because 0.8 is the probability that you don't get a Halep in any individual box, and we're doing that 4 times. And what we originally were asking is, what is the probability of getting 3 Haleps in 7 boxes? So you have 3 Haleps in 3 boxes, none in the other 4, but we determined there's more than one way to get 3 Haleps in 7 boxes. And we actually use the idea of combinations to figure out that there are actually 35 different ways to get 3 successes in 7 trials, if we're going to use more general language that would apply to any possible example here. So what we did was we took all 3 of these results and put them together. We just multiplied the 3 of them. So it turns out the probability of getting 3 Haleps in 7 boxes, we take the number of ways you can do it times the probability of success raised to the power of how many successes there are, which is 3, times, I guess you could call this the probability of failure, raised to the power of the number of failures you have. And we calculated that probability. And I teased that in this video we would determine a general model for how to calculate probabilities like this. And this is what it is: the binomial probability model. Okay? Binomial is one of several different models that you will learn about in your statistical career if you intend to keep taking stats classes. This is our first one. And what this means is, if you're asked to find the probability that the number of successes that you get is equal to a particular number, there's a formula you can use to calculate that probability, and it will work like this. But we're going to do it using any possible numbers. Okay. So, for this model, this is going to be the number of combinations, with n being the number of trials and k being the number of successes. So in this problem here, n, the number of trials, was 7, and k, the number of successes, was 3. So this was 7 choose 3. Okay? So we're going to take that number of combinations and multiply it by P is the probability of success raised to the kth power, where k is the number of successes. It's the same as this k, it's the same as this k. Okay. And then we said something about failure, the probability of failure. That's going to be called Q. And the exponent that it's raised to is the number of failures, which is actually equal to the number of trials minus number of successes. Okay, so these are exponents here. And this is the formula. It's what we just did for this problem, but generalized for any possible values. So this might seem a little over your head, potentially. Let's go ahead and define what all these letters represent. Just make things a little more clear. You've got n is the number of trials. Okay, so that number is here and here. And in this problem, that was 7. So you saw that that was here, and, well, the way we got 4 was we took 7 minus 3. Okay. So n is the number of trials. K is the number of successes. This is the only variable which reasonable statisticians differ on what letter to use for this. Some people use X, some people use R. We're going to use K. And I'm going to try to stick that as much as I can, but in my past I've used all of those, so if I use a different letter, I apologize. K is the number of successes, so in the example we did here, that number was 3. We also have P and Q here. P is the probability of success. P is the probability of success. So that will go here, and in our problem, that was 0.2. That was the probability of getting HALOP in a box. And Q is how we denote the probability of failure. In our problem, that was 0.8. These two things will always add up to 1. So sometimes instead of Q, sometimes you'll see that written as 1 minus P, because it is. Okay. Another way of writing this would be P plus Q equals 1. So if you know P, you can easily get Q. Right? And the C here stands for combinations. I'm not writing that here because that's not a variable. Okay. The variables there are N and K. That, as long as you know what N and K are, you can determine how many combinations there are going to be. Either using the formula that we talked about in the last video, or using your graphing calculator. So, now that we know the model, let's use it to answer some more questions about probability. So let's use the same setup here, but let's pretend for just a second, and I know it's painful for me, let's suppose you want to look for someone else in the boxes. I don't know why you would want to do that, but just for the sake of an educational problem here, let's say we want to know the probability of getting 2 Ronaldos in 7 boxes. Okay. The way I tackle this, instead of just going ahead and starting to fill this out, I'm actually going to write down what each of these variables is equal to at the very beginning. So I'm going to put N equals, K equals, P equals, and Q equals. And I'm going to fill out all of those for this. So N is the number of trials total. So remember, a trial in this setup is an individual box. How many boxes are we looking at? 7 total. So N is still 7. Okay, N was 7 here, N is 7 in this problem, and you'll notice it is in the next example as well. I don't know why I chose 3 examples that all have N equals 7. N could be any whole number. Okay, I don't want you to think N has to be 7. K represents the number of successes. So in order to find out what K is, you have to know what a success is for this problem. For this one, a success is actually getting a Ronaldo. So how many Ronaldos do we want? 2. So that is K. 2 successes here. So we want to know the probability of getting 2 successes in 7 trials. K is 2, N is 7. What is the probability of success? Well, a success is getting Ronaldo in a box. What is the probability of that? That's 30%. So for the purposes of this calculation, we're going to turn that into 0.3. And so Q, the probability of failure, if the probability of getting Ronaldo in a box is 0.3, what's the probability that you don't get Ronaldo in a box? Well, it's 1 minus this, right? Q equals 1 minus P. So what is 1 minus 0.3? That's 0.7. You should always add up to 1. Okay, now that we know what all the variables are equal to, now we can fill out the formula here. So, n, choose k, so that's going to be, n is 7, k is 2. Probability of success is 0.3 to the kth power, that's 2 this time, times q, which is 0.7, raised to the n minus k power, that's going to be 7 minus 2. Okay. And I will write all that out. I know that's 5, but I write it out using the model that's here, just so I know that I'm not making any mistakes. So, it's easy enough to type in 0.3 squared and 0.7 to the 5th into your calculator. The sticking point for students tends to be remembering how this works. You could use the formula with all the factorials in it. From this point on, I'm not going to go through what that formula looks like. I'm actually trying to discourage you from using it. I would rather you find out what this is using a calculator. And again, if you don't have one of these, there is a link in Canvas discussions to a virtual one of these. It works exactly like this. Okay, so anything I do on this calculator, you'll be able to do online for free, totally free. So if we want to know this, we need to go to, well, first of all, we type 7. So I've got 7 here on my calculator. To get C for combinations, that's under math. Math. And then you see this. You want to go over to PRB using your right arrow. Boop, boop, boop. And you want number 3. So go down to 3. Doot, doot. Enter. So you get 7 NCR. And then you want your 2. So 7 NCR2. That will tell you how many ways you can get 2 successes in 7 trials. And it's 21. So this is 21 times 0.3 squared times 0.7 to the 5th. Okay, so 21 times 0.3 squared times 0.7 to the 5th. I get 0.318 if I round to 3 decimal places. 0.318. Okay. All right. And just so we're clear, this is the probability of getting exactly 2 Ronaldos in 7 boxes. If I wanted to know the probability of getting 2 or more, that would be different than this. Okay, that number would actually be higher than what we got here. And we will deal with questions like that in section 3. So that would be another week or 2. Okay, so keep that on hold. Right now, we are only using this model to represent the probability of getting exactly 2 or exactly 3 or so on successes in a given number of trials. Okay, this is the next example. Still based on this setup, we want the probability of getting essentially all LeBrons in 7 boxes. So what I think you should do, based on the 2 examples that we've done so far, see if you can tackle this one on your own. Pause the video, try it out, see if you can get the answer. Come back when you're ready. end up with about 0.008 for that. So going through this a little more slowly, first thing I did was write out what all my variables are equal to. For any problem where you're using the binomial probability model, which, by the way, would be any problem where you know you've got those binomial experiment conditions met. If you asked the probability of something happening, you'll want to know what N, K, P, and Q are, so you can write out the model. So N and K are both 7 here, because there are 7 trials, and we want all of them to be successes. The probability of success, LeBron, is 50%, so the probability of failure is also 50%. This is a 50-50 shot in any individual box of getting LeBron. So we want to know essentially what's the probability of getting 7 coin flips in a row going the way we want. So that's set up here. We want the number of combinations with N and K both 7 times 0.5 to the 7th power times 0.5 to the 7 minus 7th power. Again, these are both 7 because N and K are both 7. 7 choose 7, that's the number of ways to get 7 successes in 7 trials. There's only one way to do it, and that's if every single trial is a success. So if N and K are ever the same number, that's going to equal 1. So that can be a nice shortcut. I would still type it into the calculator, though, just to make sure. 0.5 to the 7th, this becomes 0th power. And you'll notice something interesting here. First of all, this is 1, so it's not really contributing anything. This is 0.5 to the 0 power. Any number to the 0 power is just 1. So this whole model boils down to just 0.5 to the 7th power, which gives you this, ish. I rounded a little bit. Okay. So, hopefully now you're a little more comfortable. If you're given a setup and you want to know the probability of something happening, if you've got a binomial experiment, write down what each of your variables is equal to, plug them into the model, and off you go. So with that in mind, let's try this one out. Completely different setup. Let's see if we can get the answer. This might be a little tough to read. Sorry about my setup here. I'm struggling to find a better way of doing this that you can actually read everything easily. The Mars Company gives M&Ms a twist. So the Mars Company pumps out M&Ms. They want to come up with something new here. 30% of M&Ms will turn your tongue its color. Okay, this is not real. This is only in my imagination. I would totally buy these, by the way. Okay, 30% of M&Ms will change your tongue its color. These M&Ms are distributed evenly among bags. So you get a bag of M&Ms from the store, and it says, hey, tongue-changing M&Ms inside. You can assume about 30% of them will change your tongue whatever color the M&M is. So you buy a bag because you're excited, and you choose one at a time to eat. So you're not taking a whole bunch and throwing them in your mouth because the whole fun is figuring out which of the M&Ms are the tongue-changing ones. Okay? So, what we want to know is, what is the probability of finding 2 of those tongue-changing M&Ms in a set of 5? So you're going to eat 5 of those M&Ms, and you want to know what the probability is that 2 of them, exactly 2, are tongue-changing M&Ms. We can answer this using our model. One of the best pieces of advice I can give you if you struggle with word problems, first of all, you are not alone. I hate problems like this. I just do. I wish I could just plug in numbers and use the formula and be done. It doesn't tell us what's what here. So make that your first step. Using the information you have, see if you can come up with these 4 things. If you can, this problem is no different than the ones you just did. Okay? So, I encourage you, take a look at this and see if you can come up with what N, K, P, and Q are equal to. this is what I have. Okay. I got N and K from the question. Okay. N is the number of trials. So a trial here is each individual M&M. Does it change your tongue or not? There are 5 M&Ms you're looking at, and the number of successes you're looking for is 2. N and K will usually be within the question. Okay? P is the probability of success. You have to determine, based on the problem, what is a success? Well, what is it you're looking for? You said there are 2 successes. What does that mean? That's the number of tongue-changing M&Ms. So P would be the probability that a given M&M is a tongue-changing M&M. What is that probability? 30%. So P is 0.3. And to get Q, it's just 1 minus P. So 1 minus 0.3 will give you that 0.7. So, once you've got N, K, P, and Q, it's as simple as using the model to come up with the answer. So, let's do it. We want the probability that X is equal to K, which is 2. Okay. I didn't write this part of the setup of the model for these examples because I already had the statements here, but this is what that would look like. We want the probability that the number of successes is 2. And that's going to be equal to, now we've got this to deal with. We know we're going to be dealing with the number of combinations first. N is 5. K is 2. So this is 5, choose 2 now. We want P to the K power. P to the K power. So that's 0.3 to the second power. And then Q to the N minus K power. Q to the N minus K. I know everyone wants to treat problems like this differently. You go about it your own way. But I cannot stress enough the importance of writing this down first. Once you've got all of those, it's just plugging and chugging until you get to the answer. So, now the problem is getting from this to your decimal answer. If I choose 2, trusty dusty calculator, 5, math, PRB, NCR, 2. Okay, what my calculator is telling me is there are 10 ways to get 2 successes out of 5 trials. This is 0.3 squared, and this is 0.7 to the third power. So I just need to calculate this. 10 times 0.3 squared times 0.7 to the third power, and I get the same thing I got last time I did this problem, which is really good. 0.3087. Or 30.87%. So there you go. It is possible to do problems like this. I don't want you to look at a word problem and immediately shut down and think, that's impossible. Every problem that you could possibly get from this section that is a word problem can be boiled down in this way. Once you've got these 4 values, which should be in there somewhere, it's just a matter of using the model to find your probability. Okay, so that's all I really want to get to in this video. There is an easier way to use this model to come up with the answer to problems like this, and I've been going back and forth. I still haven't totally decided. I think I'm going to make a separate video before part 3 that just goes over how to use the calculator for all the different things you need in this section and chapter. Okay, and I need to make it a separate video because I don't know how to edit, and I'm going to do it using the online calculator. So I will show you how to do everything you need using the online calculator. I think I'm going to do that. If I don't, I apologize. Okay. So I'm going to do that, And then there will be one more video in this section. We're going to go through another example, but in preparation to do that, you might want to know how to use the calculator to do this even easier than what we've been doing. But for now, that's all I've got, and we'll see you in the next video. Have a good day.